Thanks, and good morning, everyone. And I thank the organizers for the invitation to this conference. So, as you said, yeah, I will present my work on the definition and the construction of a non-Euclidean Newtonian limit of general relativity. This work is mostly motivated by cosmology, where Newton's theory is often used to construct cosmological models. But these models have necessarily an Euclidean topology, which is required by Newton's theory, which corresponds to a restriction with respect to general relativity. So in this sense, it would be interesting to define a theory which is locally equivalent to Newton's theory, but allows for non-Euclidean topologies. We would call such a theory a non-Euclidean Newtonian theory. We can already give an example of such a theory by taking the Poisson equation and changing the metric to feature a non-zero Ricci curvature. So for instance, if we take it to be proportional to the scalar curvature, we would allow for either spherical or hyperbolic topologies. With such a Poisson equation on scales small in front of the scalar curvature, this Poisson equation would reduce to the flat Poisson equation, and we would have a non-Euclidean Newtonian theory as I defined here. The problem with this approach is that it's purely heuristic and not justified from general relativity. And in this sense, it would be interesting, and we want to derive the non-Euclidean Newtonian theory from a limit of general relativity. So if we choose to adapt existing limits, there are many choices because there are many ways to define Newtonian limits. And in this work, I choose to adapt a well-defined limit, which is a limit of a one-parameter family of solution of the Einstein equations, which is called the geometrical limit. This limit is a limit from a manifold equipped with a Lorentzian structure to a manifold equipped with a Galilean structure. I will present precisely what are those type of structure, but basically they are invariant under Galilean transformations. This limit was introduced by Künzle and Dautcourt, firstly, to derive the Newton-Carton theory from general relativity, and later by Ehlers to define his frame theory, which is a generalization of general relativity and Newton-Carton. So from this choice of limit that we want to adapt, we can refine the definition I gave for a non-Euclidean Newtonian theory to be a theory having non-Euclidean spatial topology and defined on a Galilean manifold. In this sense, the Galilean invariance is taken as a fundamental principle of Newton's theories, whatever the topology we consider. So I will first define and present what are Galilean manifolds and the Newton-Carton theory, which is defined in such manifolds. We will then see how we can construct a limit from a Lorentzian structure to a Galilean structure. And we will then suppose that this Lorentzian structure is solution of the Einstein equation, which will give us the non-Euclidean Newtonian limit. Okay, so Galilean manifolds, these are four-dimensional manifolds, which are equipped with a Galilean structure, which is composed of a space metric, which is a rank-free symmetric twice contravariant tensor, which I denote H here, a time metric, which is a closed one form denoted tau, such that they are orthogonal, and a connection which is compatible with those two metrics. Those two metrics are invariant under Galilean transformations, and they define what we can call an absolute space and an absolute time in the manifold M. In this sense, this corresponds to the Newtonian picture of space-time. So the Newton-Carton theory is constructed on such manifolds, and instead of and relates the matter content with the space-time geometry of the manifold. This can be in the same way than general relativity.
Question, Quentin?
Yeah.
I mean, surely this Galilean invariance, this is something you have to impose on top of it, right? I mean, H and tau have to be invariant for, that's an extra assumption. It's not automatic at this stage.
No, additional. Actually, if you Actually, if you analyze Galilean transformations, you can show that they let invariant such a tensor here and such a one form here. And so you take those one form so that, yes, as you said, so that they are invariant under Galilean transformation. But no, it's automatic. I mean, it's Galilean transformation once you assume that your spatial coordinates corresponding to those Galilean transformation corresponds to the with respect to the space metric H.
Well, what I mean is, if you take your H to be a metric on a sphere, then of course it's not going to be. I mean, Galilean transformations are normally translations and rotations, right? So if you take your H to be a metric on the sphere, it's not going to be an invariant under Galilean transformations,
I mean,
unless you understand them differently.
It's purely local. It's not.
So it's only at the level of the frames or something like that. You mean the rotations or?
Yeah, those Galilean transformations. It's on a frame on just one tangent space. So it's purely local. You have one.
So Galilean transformations only mean rotations in the frame or something like that.
Yeah.
Okay.
Yeah. I don't know if I'm clear, but.
Okay, thanks.
Okay. Yeah. Okay, so Newton-Cartan theory, as I said, relates the matter content of the manifold M here with its space-time geometry, which can be seen with this second equation, which feature at the right the matter density and the left the Ricci tensor of the Galilean structure, the Galilean connection. If we take those equations and we spatially project them, and firstly suppose that we have an isolated system in R3, then we end up with the classical Newton equations, which instead of relating geometry with matter, they relate a gravitational vector field with the matter content. If instead of supposing an isolated system, we suppose an Euclidean compact topology, so it's necessarily Euclidean because the spatial curvature induced by those equations, so the curvature related to the space metric is the Ricci curvature is necessarily 0. Then you end up with the same equations with additional terms related to variable h, which corresponds to the expansion rate of the compact space. This variable is a fundamental field appearing in Newton-Cartan. And as the non-Euclidean Newton theory will be a sort of generalization of this Newton-Cartan theory for non-Euclidean topologies, it will feature this expansion rate, which threatens the approach as we will want to apply this theory, as I said, for cosmological models. So Newton-Cartan was first constructed from Newton's theory by Carton in 1923, but it was later derived from general relativity by Dautcourt and Künzle, using this construction of a limit from a Lorentzian structure to a Galilean structure, when we take a Lorentzian metric and assume it can be decomposed into Lorentz series of a parameter E, which is 1 over C square, such that the contravariant components at leading order corresponds to the space metric and the covariant components corresponds to the time metric. At leading order, the coefficients of the Lorentzian connection become if we consider this expansion, become the coefficient of connection, which is compatible with the two metrics and is a Galilean connection. And we can also show that the four-Ricci tensor of the Lorentzian connection becomes at leading order the four-Ricci tensor of the Galilean connection compatible with H and tau. In this sense, a manifold which is equipped with such a Lorentzian structure at leading order becomes a manifold equipped with a Galilean structure. Because this Galilean structure is derived from a Lorentzian structure, it is constrained by this equation, which I recall was the third of the Newton-Cartan equation, and when spatially projected, corresponds to the conservation of vorticity. This is a purely geometrical constraint. But what is really important is that there are no more constraints on this Galilean structure, and especially there are no constraints on the spatial curvature of the space metric of the Galilean structure and its spatial topology. Additional constraints, especially on the curvature, will come only from the Einstein equation. So let's take this, consider this Einstein equation and take the leading orders of the Einstein of this equation on the left-hand side, which will give us what are the leading orders of the stress energy tensor as function of the Galilean structure variables. We can then show that this stress energy tensor needs to feature a -1 order, which is proportional to the space curvature, scalar curvature of the space metric, and 0 order, which feature 2, for now, unknown terms, a variable E and a vector Q, which by analogy with the usual decomposition of the stress energy tensor can be called a heat flux, and again by analogy, a anisotropic stress, which is proportional to the Einstein tensor of the free curvature. I forgot to tell that the hard variables are related to the Galilean structure. So for now, because E and Q in this limit are unknown, and especially we don't know the relation with the matter density, the equations at leading order are not closed, and we don't have the non-Euclidean Newtonian theory we want. For this, we need to suppose what is the full order of the stress energy tensor. We can first take the standard hypothesis for the limit, which is to assume that we have the usual dust stress energy tensor, dust form for the stress energy tensor. This hypothesis was made by Künzle, Dautcourt, and Ehlers, and leads to a leading order, which is proportional to the density, implying that E can be associated to rho, Q to 0, and the free curvature is equal to 0. We can then show that we retrieve the second Newton-Carton equation, which I will not detail in this presentation. So this standard geometrical limit, to my knowledge, there is no study on of the existence of such a limit for general solution of the Einstein equation, but only for specific solutions, and this was done by Ehlers in 1997. But what is really important here is that once we make this assumption here, then the spatial curvature is necessarily 0, implying that the topology of the spatial section related to the Galilean structure is necessarily an Euclidean topology. It's not what we want, because we want spatial sections that have non-Euclidean geometry. So we see that it's not possible to take this assumption, and we need to impose at the limit that the curvature of the space metric is a non-zero, implying that we are allowed to take to assume non-Euclidean geometries. As I said, this is not compatible with the usual form of the dust tensor, and actually, because there are these additional leading order terms depending on the curvature, we need to add an additional term in the dust stress energy tensor, which at leading order will feature those two curvature terms. These leading order terms can be interpreted for the first one to be an energy curvature proportional to the space curvature, and an anisotropic stress curvature for the second one, which is proportional to the Einstein tensor of the spatial curvature. But once we see that from this, if we want non-Euclidean topologies with this limit, we need to add a term. The limit is still not closed, because we don't know the relation between E and the density rho. So we need to assume, as with the usual the standard limit, what is the full order of this additional required term. But before doing this, we need to understand why it is here, actually, because we never considered here before. So we can follow this line of interpretation by saying that adding this term in the dust stress energy tensor corresponds to a generalization of the stress energy tensor for a dust fluid, which in particular allows for a non-Euclidean Newtonian limit. if we follow this interpretation, then the fluid, which is given by the 4 velocity u, needs to be geodesic, because it's called a dust fluid, which needs to be implied by this conservation equation, even with this second term. So from this, we can make first guess to what should be this second term at full order by taking the knowledge of the standard limit and assume that E is equal to rho and Q, the heat flux, is equal to 0, and we associate tau, the time metric, to be the 4 velocity of the fluid as made with the standard limit. We would get in this extrapolation this form of the stress energy tensor, which we can check leads to the geodesic equation. The problem is that there are many more guesses, many more extrapolation we might propose that leads to the geodesic equation and leads to the same leading order terms. And the problem is that the non-Euclidean Newtonian theory will depend actually on this extrapolation. So we are not able to give this theory for now, and we just know that we have to add an additional term in to have it in the stress energy tensor. So during this presentation, I proposed a way to define a non-Euclidean Newtonian theory from a limit of general relativity, a geometrical limit. We saw that if we want this limit to feature a non-Euclidean spatial topology, it requires an additional term, this dust stress energy tensor, which still needs to imply the geodesic equation at full order with the conservation equation. The perspective would be to study further extrapolated stress energy tensor at full order and try to find the right one, the most physical one, if there is one, which would finally give us the form of the theory at full order, which would be a powerful tool to study the effect of topology in structure formation and expansion. So thanks for listening, and if you have any questions, please.
Thank you. Thank you very much for the presentation. We had some few minutes for questions. So anyone, you can ask questions in the chat in the QA session, in the QA section also.
Maciek, I have a remark about this.
Yeah.
May I?
Sure, please.
Okay, so I want to say that you included also cosmological constant, but in the case of when you think about non-relativistic limit of de Sitter, because you know this is roughly non-relativistic or Newtonian limit of Minkowski, roughly.
It's not actually. It's not Minkowski.
I know, but
yeah.
Let me say, but if you start with another symmetries with de Sitter, there is another opportunity to pass to the non-relativistic limit, which is called Newton-Hooke spacetime, and this means, and this was discussed a little yesterday with some equations, but the geometric, let's say, structure is this Newton-Hooke spacetime, and then you have a Galilean analog, which is also sometimes called Newton-Hooke. So I just want to address that maybe it is nice to understand also these structures. And this is just a remark. You know.
So if I understand it correctly, I mean, this had to do with the way how you go with lambda to 0 when c goes to infinity, right?
Exactly,
and so
exactly.
In your equation, would this mean that
it would be not all the epsilon square, but rather epsilon in this limit, you know.
Do you have a feeling what would happen with your equation? Would lambda just vanish from the equations, or what?
Here,
yeah.
For this not actually this does not change. No, this does not change anything in the discussion. Actually, this lambda goes into this e here.
So this is it not exactly what you were referring to, Jacek, that you take lambda going to 0? Is Piotr there? Maybe he can just confirm. Piotr Bizon? No.
Yes, what Jacek is talking about is that lambda times c squared goes to a constant.
And in this language, is this what happens or not?
I don't know the relation to
Actually,
to Newton Carton theory. So
here this does not go e square times lambda does not is not a constant at the limit, because the limit of the covariant components of the space-time metric is minus it's just an epsilon here, is a -1 order actually, and so this epsilon cancels with the epsilon which is here in the metric. So actually it's an epsilon and not an epsilon square.
Yeah, but you keep lambda constant, right? When you take
lambda is constant, yeah.
So
yeah, lambda
it's a different limit.
actually, because lambda is also featured in Newton's theory. I just keep it constant. For instance, here you end up with this equation, which is purely Newtonian, where the same lambda features actually. So yeah, lambda doesn't change, just this changes.
So in this limit that Piotr mentioned, it will just vanish from the equations probably.
I suppose, yeah.
Now, so you took the geodesic equations of kind of fundamental equation because maybe it's the equivalence principle or something like that. But maybe maybe there's a more natural, there's another natural equation which could be thought of in this context. I have no idea, but what? And
actually, another equation I would like to preserve, but I'm not sure, is the mass conservation in the form of nabla applied to rho times u. And for instance, this form here doesn't preserve necessarily this conservation equation. But I'm not sure at which point we should necessarily keep this conservation of rho and not a conservation of rho plus rho r. For the geodesic equation, it's sure, but yeah, I think there are more
some options here. Thank you.
Okay, thank you. So thank you for nice presentation. We move on with our schedule.